Did you know that the microcontaminants called sludge and oil are the cause of machine failures and oil leaks? Let's take a closer look at the microcontaminants found in hydraulic fluid under a microscope. This is hydraulic fluid from a flow-forming machine. Here we can see jelly-like sludge. If you rub a needle against a permanent magnet, the needle will become magnetized. Then, if we dip this magnetized needle into the sludge coagulates and is drawn toward the needles. This is a contaminant found in a hydraulic fluid of a die casting machine. This too is in the form of fine jelly. Similarly, this contaminant also is drawn to our magnetized needle. With this large injection machine, the lead intended contaminant, whose hydraulic fluid additive has changed, is also drawn to the magnetized needle along with other contaminants. Sludge causes blockages which damage filters. This is an expanded photograph of blocked filter mesh and the adhering sludge. Photos show the inside of an oil tank of hydraulic equipment. You can see the contaminant, called sludge, adhering to the inner walls. By removing the maintenance inspection side cover, we can observe that brown sludge is completely adhering inside. The rotor rotates for the vane pump used here, causing reciprocating movement of the vane whereby oil is fed. By disassembling this pump, we learned that sludge acts like an adhesive, causing the vane to bond to the rotor, resulting in pump failure. Let's zoom in on a sludge adhering to the vane. This resin-like sludge colors the parts and causes friction. It can also solidify into a plastic-like material, making it impossible for the machine to run. An analysis of this sludge reveals that it is composed of trace quantities of metal and minerals, semi-solid metric soap, and liquid organic acid. This photograph showed the sludge seen under a microscope. We see that it is composed almost completely of the degenerated material of oil that arrows like to pass through, and only trace amounts of solid particles such as metal or dirt that do not allow light to pass through. That the leaking of oil contributes to the mechanical friction found, but most frequently the cause is contaminated or dirty oil. The organic acid and hydrosulfide with a component of sludge cause corrosion of the seals and of metal surfaces of areas of friction. This is an O-ring used in dirty oil. The grooved areas of corrosion are quite well defined. A vertical section of this part reveals a corrosion caused by chemical reactions. If we compare the seal of an oil ring used for 4 years in a system that has clean oil with a new oil ring, we see no change in its ability to seal, although there has been some friction. What effect does the degree of clean oil have on the friction of the metal parts of a machine? Let's take a look at a solenoid valve used in hydraulic equipment. A part called a spool for switching the flow of the oil is dispersed in the solenoid valve. This has a reciprocating action. This is a microphotograph of the surface of the spool action. Let's first take a look at a new spool. This spool has vertical processing scars in the circumference direction made during the manufacturing process. The spool used in a dirty oil environment has severe horizontal scars in the operating direction. The scars are so deep that it is almost impossible to see the processing scars in the circumference direction. The edges of the operating portion were at right angles, like a new part, but here you can see that it has lost the corners. This is the result of the oil pressure and closing wear. What would happen if clean oil were used? This oil press has been used maintenance-free without any breakdowns for approximately 10 years. The oil used in this machine has maintained a degree of cleanliness higher than new oil for approximately 10 years, yet it has never been changed. We investigated the operating surface of the spool that has worked without failing using this oil 10 years after it began operation. As you can see in this microphotograph, there are no horizontal scars in the operating direction, and the vertical processing scars of when the part was new, shown at the hour, still remain. When this is compared with a new part, it is easy to see that there is extremely little friction and it has a smooth operating surface. This is a microscopic view of the reaction of the contaminant in dirty oil to a magnet. When we insert our magnetized needle into the oil, microsludge such as the degenerated material of oil dispersed in a solid form coagulates into a jelly. This shows sludge gradually adhering to the magnetized needle. If the proper magnetic field is dispersed in a tank, and the conditions are right for sludge to disperse, the oil can be cleaned in the tank. This is the cleaning tank system. This is an ordinary tank. In the tank, the oil return and suction portions are in close proximity, so the oil is stirred, which disperses and propagates the amount of sludge. This causes oil contamination to progress. Let's modify this tank and transform it into a cleaning tank system. First, a separator plate is added to separate the oil return and suction portions into the end of the tank. Also, the oil return pipes will be collected at one location. This configuration prevents the oil from being mixed, and allows it to flow without agitation, thereby making it easier for the sludge to coagulate and to precipitate to the bottom. Next, we will place a microseparator at the center of the tank, where the flow has precipitated and generate a wide three-dimensional magnetic field. The oil will travel through the magnetic field of the microseparator, thereby being cleaned inside the tank. The quantity of microseparators used in the cleaning tank system should be determined by considering conditions such as the structure and capacity of the tank, the QP ratio, pumping pressure, and type of oil used. The microseparator plays an important role in the system. JIS calls this a magnet separator, but we jointly developed it with Nippon Steel Corporation Yahata Works. This shows sludge adhering to the surface of the microseparator. If we zoom in on the sludge separated from the oil, we can see that it has a stick, tacky nature. Let's take a look at the magnetic field under an electron microscope. The degenerated jelly-like oil that includes magnetic particles has started to collect in the magnetic field. This grows larger in time. As you can see in the video, the magnetic force of the microseparator draws the sludge toward it, thereby cleaning the oil. Let's take another look at the sludge reaction to magnets. This is because sludge coagulates and only a low percentage of what is separated from the oil is a magnetic substance, such as iron. For your understanding, the discussion above described how a microseparator removes degenerated matter to clean oil as a part of a cleaning tank system. Machines that employ the cleaning tank system are free from oil leaks and machine failures and do not require oil changes. They have become virtually maintenance-free. This system contributes to improved machine performance. This was a brief discussion of the cleaning tank system. Further details can be found in the technical bulletin of the Japan Society for Precision Engineering, the Japan Fluid Power Association, Oil and Air Pressure Engineering, and the Journal of Japanese Society of Tribologists. We have also issued a science news bulletin that discloses an example of an environment of the cleaning tank system to facilitate understanding of this technology. We hope that it will be a strong contribution to your business.